When managing or acquiring data, missing values are going to be a problem. Sensors break and survey questions are left unanswered, and large chunks of missing values are left behind. Despite these issues, scientists have to be able to analyze their data. To help accomplish this goal, I investigated how to best manage these missing segments in categorical sequence or time series data during my internship at a national laboratory. To help test the procedures, we used a one-time survey. The survey asked respondents about both demographical and travel information for each year from when they were 20 to when they are 50. By including respondents under the age of 50, we introduced gaps. There is no way that the respondents could know the details of their lives at 50 if they're only 35. We set out to prove that despite the missing values, we can cluster or group the demographical data to predict a respondent's travel habits. The sequence plot shown here is composed of more than 700 respondent sequences stacked one on top of the other. This particular one shows the number of children respondents had for each year from between the ages of 20 to 50. We have several more similar plots showing different. To address these missing values, we considered two strategies. The first and more standard approach is to use a grid search to optimize every parameter for improved clustering. Because our missing values all occur at the end of the sequence, we are also able to delete the missing values and normalize the sequence length without fear of destroying the alignment of the data. We used a grid search method for optimal matching parameters. Optimal matching is our distance metric that can determine how similar sequences are by comparing their components and adding an NA cost for every component that doesn't match. The default value for this cost is 2. However, when we used this cost, we found it added large artificial clusters that were determined solely by the alignment variable, age in this case. The TSNE plots shown here are colored only by age, and you can see that the position is almost exclusively chosen by this variable. To ensure authentic clusters, we continued lowering this cost until the clusters nearly disappeared. We don't consider using an NA cost of 0 because age should play some part in the cluster, just not solely determine them. So we decide to continue with an NA cost of 0.2. Determining the correct number of clusters is an extremely important part of this process, even though it has little or nothing to do with missing values. Even perfect data with 4 very natural clusters will give horrible groups if you try to split it into 7 groups. To determine the natural number of clusters, we use cluster validity metrics to determine how well the data is fitting into these clusters. We expect the data will cluster better at its natural number of clusters, so we look for unexplained peaks. We then create the TSNE plots to determine which of the peaks look best. Here, at higher number of clusters, the clusters seem to blend together, so we proceed with 4 clusters. Finally, to help mitigate some of these effects of the missing values, we look at shortening the lengths of the sequences. As you can see, most of the missing values are at the end. We shortened the lengths to remove that missing, and the artificial clusters lessened, showing that we were lowering the effects of the gap. We settled on 39 as an end length, as most people seem to be stagnant in their life choices after 40, and the artificial clusters had all but vanished. The final cluster is shown here. Though the TSNE plots are great at reducing our 50-dimensional data down to 2 easier to interpret dimensions, it still can be difficult to know what they mean. So we go back to the sequence plot. Each column corresponds to a group of points on the TSNE plot. Let's look at clusters 2 and 3 specifically. As you can see, they have similar employment, education, and partner choices. However, cluster 3 has children, while cluster 2 does not. With this distinction, these clusters separate themselves into couples versus families. Similarly, clusters 2 and 4 follow similar employment, education, and child lifetime, but cluster 4 has no partner. There is a similar distinction between every cluster. Despite missing nearly 25% of the data, we were able to determine distinct clusters. This is on an example of a smaller data set, but it could be replicated on nearly any time series data, especially using the grid search method. When possible, using the deletion and normalization structure is much preferable to the grid search method. There is a strong correlation between the demographics in our data and their travel habits.